morning all of you. Today we will look into some basics of Bessel functions, because you need to understand the solution for Bessel functions before we do the solution to the eigen value problem. So I am not going to run a class on Bessel functions, but just to prime you what should be the form of the Bessel equation, and what is the solution to a given Bessel equation, and some properties of Bessel function differentiation and integration. Okay. Now if you have any second order linear differential equation of this particular form, okay, the form that I have written here. So you have x square d square y by dx square plus x dy by dx plus this coefficient. Now this coefficient is function of x here, okay, so times y equal to 0. So this functional form of this equation is referred to as the Bessel equation after the German mathematician Bessel. So the solution to the Bessel equation is given as y of x is equal to some constant c1 times Bessel function. So you use the Bessel function. There are two kinds. One is the Bessel function of the first kind, Bessel function of the second kind. Okay, the Bessel function of the first kind is represented by the letter j. Okay, so j, and the order of the Bessel function is denoted by this value of nu here. This is any real number, and you use the nu here to denote the order of the Bessel function. This is a function of m times x, where m is the value that you have got here. So m times x plus c2. Now the Bessel function of the second kind is represented by the letter y. The order is represented by the subscript nu mx. Okay, so this is called the Bessel function of the first kind, and of the order nu. This is the Bessel function of the second kind and order nu. Okay, so this is so far to say for a Bessel function. Now you can slightly write this Bessel function in a different way. Suppose if your m square here was, instead of being a positive value, if you have a negative value here, so you can replace this with a negative sign, and you can write an equation like this. Okay, suppose your m square value has to be a negative value. In that case, then you write like this, then this becomes what is called as a modified Bessel equation. It's the same structure as the Bessel equation, only the coefficient term here will have a negative sign, and correspondingly the solution to this here, this is m, so now this will become imaginary number. Okay, once this is negative here, so this will become mi, basically an imaginary number. So instead of writing everything in terms of imaginary functions, okay, so they have introduced what is called as a modified Bessel function, okay, which takes into account naturally the imaginary part of the coefficient. So therefore for that you have a modified Bessel function solution. So where you represent the solution as c1 times the modified Bessel function of the first kind is denoted by the letter capital I, subscript nu for the order mx, plus the modified Bessel function of the second kind is represented by the symbol letter k, subscript nu mx. Okay, so these are your modified Bessel functions of the first and second kind. and of the order nu. Okay. So as far as the solution to our eigenvalue problem is concerned, I think this is all sufficient to write how to represent the solution to the eigenvalue problem. Okay. So now we will compare this Bessel equation with the eigenvalue problem that we have. Okay. So what were our solutions? Basically, when we substituted, when we used the separation of variables into the energy equation, we found out that the PDE can be reduced to two ODEs. One is a first order ODE with respect to x, so here we have assumed that the Graetz problem has originally assumed that the profile, velocity profile, is a slug flow profile. So it is a uniform velocity, the value is um, and the solution to this along the variation along the x is given by the first order ODE. Okay. And we have also seen the solution to can be written as some constant times e power minus alpha lambda square by um into x, right. So directly you can integrate it out, and the actual eigenvalue problem in terms of r was this, right. And the boundary condition for r, what were the boundary conditions to solve this second order ODE in terms of r? R at r equal to 0. Do you have any boundary condition at r equal to 0? Okay, finite, or I would say dr by dr should be 0, okay, or r at r equal to 0 should be finite, both are equivalent. The other condition, r at r equal to 1 should be 0, okay, because the temperature there at the wall is constant wall temperature, so theta has to be 0, therefore r at r equal to 1 has to be 0. So now you compare this with your Bessel equation, okay. So the original Bessel equation, not the modified one. So you multiply throughout by r square, so you have r here, here you have again r square. So now you see these and these coefficients are exactly identical, instead of x you have r, okay. Now as far as this coefficient is concerned, you have m square x square y, okay. Instead of that you have lambda square r square capital R, and there is nothing like a nu here, the nu is equal to 0. So therefore the order of the Bessel functions is 0th order, okay. So that is one thing, and your m square is equal to lambda square. So therefore the solution to this ODE will be in terms of the Bessel functions of the first kind and second kind 0th order. So C1 j naught into lambda r plus C2 you have y naught into lambda r, okay. So this is your solution to the eigenvalue problem. So this is your eigenvalue problem. So any eigenvalue problem should have two homogeneous boundary conditions, okay. So this is the solution to the eigenvalue problem. So now we apply the two boundary conditions to get the two constants, okay. So now directly we come to the condition at r equal to 0, r should be finite, capital R should be finite. So I will also show you how these Bessel functions behave. So if you draw the Bessel function j as a function of your x or r, okay. So it will start from 1 and then So this is your J0 of R, okay, and J1 will have a behavior like this, and J2 will have another behavior. So similarly, if you draw the Bessel function of the second kind, that is your y as a function of R. So this is negative, this is positive here. So the zeroth order Bessel function of the second kind will at R equal to 0 will start from infinity and it will increase to positive value and it will be oscillatory again. Okay, so this is your y naught of x, and you will find that y1 will have another behavior like this, y1 of R, y naught of R. So this is how your Bessel functions behave, okay, and your modified Bessel functions will have a different behavior. So your I versus R, so this is 0, this will always be positive here, so this will be your I naught of R, and then this will be your I1 of R. Similarly, your modified Bessel function of the second kind, that is your K function of R, so this is your K naught of R, this is your K1 of R. Okay, this is to just give you an idea how the Bessel functions. You take any Bessel function chart, you will find the tabulated values corresponding to different values of x or R. You will find the corresponding variation in the first kind and second kind, all the different orders, starting from the zeroth order, first order, second order. The zeroth order Bessel function here means it is the highest order. Okay, does not mean it is the lower order. It is the highest order, and 1, 2, 3, 4 they are the lower order Bessel functions. Okay, so now coming back to this particular eigenvalue problem. So at R equal to 0, if your capital R has to be finite, now you can see that at R equal to 0 my Bessel function of the second kind will be going to infinity, right. Therefore, in order to make my capital R finite, C2 has to be 0. Okay, so at R equal to 0 my y naught of 0 goes to infinity, so this gives that C2 has to be 0 for the solution to be finite. So therefore my R of R directly reduces to C1 J naught lambda R. Okay, so this is how my eigenvalue problem reduces. Okay, now again I can find out the constant C1 by applying the other boundary condition. So now the thing is, I should also know what is the eigenvalue here, because the eigenvalue is also undetermined. So the remaining constant, whatever is left out, that is at R equal to 1, capital R is equal to 0, that will be used to find the eigenvalue. Okay, so one of the constants is determined from the one boundary condition and the eigenvalue is determined from the other boundary condition. So this constant is not a problem, because final solution for theta I can multiply this and this into a single constant, and I can use the remaining boundary condition, that is at x is equal to 0. That is one more boundary condition which I have not utilized. So totally there are 3 boundary conditions. Okay, so that I can determine it later, but right now I can use the second boundary condition for the eigenvalue problem and determine the value of lambda here. So therefore the condition that R at R equal to 1 is equal to 0, so this should give me the fact that J1 C1 J naught lambda should be equal to 0, or in other words, so the eigenvalues should satisfy this particular equation. So that means you look at the Bessel function, so wherever it becomes 0, so these are the solution which will give you the corresponding value of lambda, right. So Oh, okay, so this should be r is equal to, sorry, not 1, r naught. Okay, these are all dimensional, so I should write in terms of j r naught here. Please correct it. So this is at r equal to r naught. These are all dimensional radii, so I should use at r equal to r naught. So therefore it should satisfy this particular equation. So the corresponding value of lambda r naught will be the ones where j becomes 0. So you can see there are several values, right? There are several places where j becomes 0. So this has now multiple solutions. Okay, so I will just give you the first few roots where j becomes 0. So let me call lambda n r naught as some factor beta n. Okay, so the zeros, so these are the zeros of j naught beta n equal to zeros of j naught beta n. Okay, so the first 6 zeros correspond to beta 1 is equal to 2.4048, then beta 2 5.5207, beta 3 is 8.6537, beta 4 is 11.7915, and then beta 5 14.9309, and the last one beta 6 is 18.071. So these are the first 6 zeros to the corresponding value of lambda into r naught. Okay. So now I have determined my eigenvalues, because these eigenvalues are all nothing but these values. So this is lambda 1 r naught, lambda 2 r naught, lambda 3 r naught, and so on and so forth. You can have many number of solutions, but I have given the first 6. These are the most relevant. Okay, the other ones will be of the lower order, which you can neglect. All right. So I will give you 2 more properties when you differentiate and integrate the Bessel functions, which are important now. So I will give you the derivative identities of the Bessel function. So I will call this as derivative identities. So the identity number 1, if you differentiate the 0th order Bessel function of the first kind, that is your j naught lambda n r, so that gives you minus lambda n j1 lambda n r. Okay, this is your first identity. The second identity, if you differentiate r into j1 lambda n r, so if you multiply r with the Bessel function of the first order, okay, the first kind Bessel function of the first order, you will be getting lambda n r into Bessel function of the 0th order, lambda n r. This is your second identity. We will use all these identities. So number 3 is the fact the Bessel functions have another important property, that is the principle of orthogonality. Okay, so if you look at any eigenvalue problem, and you determine any eigenfunction, so in this case the eigenfunctions are Bessel functions of the first kind of the 0th order. These are the eigenfunctions, right? So these are the corresponding eigenfunction to the eigenvalue problem. Okay, so this is your eigenvalue problem. So the solution to R is in terms of Bessel function of the 0th order of the first kind. So these are your eigenfunctions. Now any eigenfunction, any eigenvalue problem where you determine your eigenfunction should satisfy the principle of orthogonality. Okay, we will see that is very useful to determine the remaining constant. Okay, now that principle of orthogonality for this case can be written as 0 to r naught r j naught square dr is equal to r naught square by 2 j1 the whole square. Okay, so this is another important property. When you integrate, you multiply r with j naught square lambda n r, so you get this particular expression. Okay, so this is another thing which you should remember. Now the principle of orthogonality states that if the eigenfunctions are orthogonal, if you integrate them, if you multiply an eigenfunction j naught lambda n r with the eigenfunction lambda m r, so n being different from m, so these are different integers. Okay, so your n may go from 1 to 3 and for a fixed value of m. Okay, now if you multiply these two eigenfunctions and you also multiply r, okay, and if you integrate it, this will be equal to 0 if m is not equal to n. This is the principle of orthogonality. Okay, so only if m equal to n, the eigenvalue integer corresponds exactly same, so then only you have some finite value, non-trivial value. So this will be equal to 0 to r naught r into j naught lambda n r the whole square into dr if m equal to n. So this is the principle of orthogonality basically. So that means, see, these eigenvalues are like principal directions, like your x, y, z Cartesian directions. So these represent the variation of solution in those principal directions. So if you multiply the solution corresponding to one principal direction to another, so those two are mutually orthogonal directions, so therefore the product will be 0. Okay, so whereas if you multiply in the same direction, then this is where you get a non-trivial solution. So this is where the principle of orthogonality plays importance, and when you are integrating this 0 to r naught r j naught square, we will use this particular identity here. Alright. So now we will erase this, we do not require. Is the principle of orthogonality clear? I think if you take any course on linear algebra, I think you will be taught this. It is like saying your I dot I is equal to 1, your I dot j equal to 0. So these are mutually orthogonal directions. So the eigenvalues correspond to principal directions which are mutually orthogonal, and the eigenfunction should respect that orthogonality. Alright. So now we have all the necessary background, therefore you can write your solution for theta x comma r. So you have to now tell me what will be the solution. This is nothing but according to separation of variables, and now we found the solution for both x and r. So how can we write it? So let us multiply c1 and c and call this as another constant c, okay, some constant c or maybe a or whatever you want to call. Let me, I have used in my notes as a, so I will use a, and what is the remaining? J naught lambda r, c1 j naught lambda r is your eigenfunction, okay, and what is the remaining part? X of x will be e power minus alpha lambda square by umx. See, finally your solution reduces to this. So in terms of x it is exponentially decaying function. Your theta starts at 1 at the inlet where the temperature equal to Ti, and then somewhere downstream your temperature should approach the wall temperature, therefore the difference should become 0, T minus T wall should become 0. So that is your exponentially decaying function with respect to x, right. Now with respect to r it is a Bessel function variation. Now you see that when you found out the eigenvalues you had multiple eigenvalues, right. So you had, first I had written down the first 6 eigenvalues, okay, but there are multiple eigenvalues and they are all solutions. So then how do you include them? So you assume that they are all linearly superposed and you can denote your final solution as a summation of all those from n equal to 1 to infinity, and you have lambda n, okay. So this is your final solution, so which is a linear superposition of all your solutions for different values of eigenvalues. For each value of eigenvalue you have a particular Bessel function, you have a particular exponential term. So like that for each lambda 1, lambda 2, lambda 3 you now get all the values, sum them up, so that will give you the final value of theta. Of course the first few terms will be the significant terms, the first say 3 or 4 terms, after that they will be insignificant, and even if you do not include them it is not going to change the solution much, okay. So therefore this is your final solution, and now the thing is how do we calculate the remaining constant a. So this a also becomes an, so corresponding to each value of lambda n you have particular value of this constant an. So now how do you calculate this constant? Now we use the remaining boundary condition for theta, x is equal to 0, right. So theta at x is equal to 0 at any r should be 1. Now how do we apply this boundary condition here? So therefore we say that summation n equal to 1 to infinity an j naught lambda n r, and this becomes x is equal to 0, so that will be 1. So this should be equal to, but still we have not determined what is an because this is within the summation. So now we make use of the orthogonality principle, okay. So what we will do is we will multiply both sides with j naught lambda m r, where m is different from n, okay, and integrate them. So for orthogonality condition in this case of Bessel function you should be having r into j naught lambda m r. So we will multiply both sides with that. So we have 0 to r naught. So my right hand side I am writing on the left hand side here, I multiply with r j naught lambda m r dr, that is my RHS, right. On the LHS I have this 0 to r naught summation n equal to 1 to infinity an into r into j naught lambda n r j naught lambda m r into dr, okay. So now of course it has to satisfy orthogonality condition here, therefore for any values of m which is not equal to n this will be 0, and this will be equal to r j naught lambda n r the whole square dr for m equal to n. So only there it will be a non-trivial solution. So therefore this will become 0 to r naught so for m equal to n, so only then, so you can imagine the summation here. So now I sum from n equal to 1 to infinity for a given value of m. If your n is not equal to m, so those values are all 0. So therefore this summation will reduce to the fact that it will be equal to j naught lambda n r the whole square only for m equal to n. So that should be an into 0 to r naught r j naught square lambda n r dr. Okay. So now you understood. So this reduces to this particular expression here. So the summation is now gone, because for m not equal to n, so those values are all 0. So the final whatever remains is where your m equal to n. So your summation is now removed, and from here directly you can calculate the value of an. So this gives an as 0 to r naught j lambda n r dr divided by 0 to r naught r j naught square lambda n r dr. Okay. So now we have to simplify this further. So that is where we make use of the derivative identities. So numerator integral r j naught lambda n r. So you integrate both sides. So that should be equal to r j1 lambda n r, right? R j1 lambda n r divided by lambda n, and now you have integral r j naught square lambda n r. So that is, you use this identity number 3, that should be r naught square by 2. Now of course when you integrate it you have to apply the limits here. This is between 0 to r naught, and when you integrate this from 0 to r naught you directly get this particular expression r naught square by 2 into j1 square lambda n r naught. Okay. So at 0 j1 will be what? 0 if you look at the curve. So therefore this will be r naught square r naught into j1 lambda n r naught divided by r naught square by 2. So this j1 cancels here, r naught cancels. So this can be written as 2 here, r naught and j1 lambda n r naught. Okay. So this is your expression for an, final expression. So therefore you can substitute this into the, let me call this as number 1 for an, you can substitute, and then you can write the final expression for theta as so 2 can be taken out, summation n equal to 1 to infinity 1 by lambda n r naught, you have j naught lambda n r divided by j1 lambda n r naught exponential minus lambda by um alpha by um lambda n square x. So this is your final solution. Okay. What we can do is we can cast this into a completely non-dimensional representation, okay, so that you do not work in terms of x or lambda, but something like lambda and r we have already used the notation beta, okay, and even we will non-dimensionalize this term. So how I am going to non-dimensionalize is the following way. So I can write this minus alpha by um lambda n square x as, I can write this as minus alpha by into x by r naught square. So I am multiplying and dividing by r naught square, so lambda n r naught the whole square, okay, and I am also going to rewrite this a little bit as so I can write this as x by d naught into alpha n r naught the whole square divided by d naught by alpha, that is a factor of 4, okay. So this r naught square I have replaced this by d naught square by 4, okay. So and I am grouping x by d naught as one non-dimensional term, and now I am left with d naught by alpha. So what is d naught by alpha? Reynolds number times Prandtl number, okay. So therefore I can replace this entire thing as a non-dimensional group, which is minus 4 x by d naught lambda n r naught. I have used the notation beta n, okay, because lambda n has the units of what? What is the unit of lambda? 1 by r. So therefore lambda n r naught will be a non-dimensional group, okay. So that therefore I replace that with beta n square divided by re into pr. Now I use another non-dimensional group called Peclet number, which is the product of Reynolds number times the Prandtl number, which is nothing but d naught by alpha, okay. So generally rather than all the time doing REPR, so people refer to that as a Peclet number, so the product of Re times PR. Therefore in terms of the non-dimensional form, you can describe your theta as twice n equal to 1 to infinity 1 by beta n j naught. Now how do you write this? Lambda n r. So you divide and multiply by r naught, so then that will become beta n times r by r naught, okay, divided by j1 beta n, okay, into e power, this entire thing can be written as minus 4 x by d naught into lambda n r naught is nothing but beta n square divided by Peclet number, okay. So this is completely non-dimensional. So once you know the particular value of Peclet number that you are solving, so that directly has both Reynolds number and Prandtl number, for different values of non-dimensional r by r naught and different values of non-dimensional x by d naught, you can directly get the solution for theta. So everything is now non-dimensional, okay. So you can plot the solution for theta as a variation with respect to r by r naught and x by d naught for a given value of Peclet number, okay. So once we got the solution, now still we are not done. So ultimately we need to find what is the Nusselt number, expression for Nusselt number, right. So therefore for Nusselt number we need to do a little bit further work, further quantities are required, okay. The first quantity, now when you define Nusselt number here, so your Nusselt number is basically h into d by k. Now you should be careful here that in the case of thermally developing flow, your h is not a constant, h is a function of the axial location. So this should be strictly speaking h subscript x, okay. So now that you define this as k dt dr at r equal to r naught into d by k into t wall minus t mean, this is how you express your heat transfer coefficient, wall flux divided by temperature difference. So now I can substitute in terms of non-dimensional theta. So theta is defined as T minus T wall by Ti minus T wall. Okay, so I can write this numerator as now minus k into d theta by dr r equal to r naught times Ti minus T wall into d divided by k times now T wall minus T mean. So I can define theta mean as T mean minus T wall by Ti minus T wall. So I can write T mean minus T wall as Ti minus T wall into theta, so into theta m. So k into theta m into T I minus T wall. So already I put a minus sign because this is T wall minus Tm, I am putting minus of Tm minus T wall. Okay, so this cancels right here, and of course your k cancels. So this will be, so left with nu x is equal to minus d theta by dr at r equal to r naught into d by theta m. So therefore now to calculate your Nusselt number, what are the quantities that you need? One is your mean temperature theta m, the other is your derivative at the wall. So you have your temperature profile, now we can calculate these two quantities. So first we will calculate your mean temperature. So very quickly we will do that. So your theta m is nothing but your Tm minus T wall by Ti minus T wall, that will be what? So you integrate, you take the mass weighted average of theta m of theta into r into u so this will be theta into u into r dr, of course you have 2 pi divided by integral 0 to r naught, you have 2 pi u of r dr, right. So this is your, this is how you define your bulk temperature or mean temperature, mass weighted average. Okay, now in your present case your u is a constant, this is a plug flow case, so therefore the u can be taken out of the integral and cancelled off straight away. So integral 0 to r naught r dr will be r naught square by 2. Okay, so this can be written as 2 by r naught square integral 0 to r naught theta r dr. Okay, now if you substitute for theta from the final expression that we have, you can write your theta mean as 4 times n equal to 1 to infinity 1 by lambda n r naught cube 0 to r naught j naught lambda n r divided by j1 lambda n r naught into e power minus lambda by um into lambda n square x. So I am just substituting for theta and multiplying with r here. Okay, so you can just verify it, I am going a little bit fast, but it is straightforward, there is no difficulty here. So integral 0 to r naught j naught lambda n into r, so already we have that identity, so that will be r into j1 lambda n r divided by lambda n. So if you put that and you manipulate it, finally you get your expression for theta m as 4 times, you please check this, 1 by lambda n r naught the whole square into e power minus lambda by um lambda n square x. So this is the final expression for theta m that you will be getting. Okay, so if you if you just use this identity and then you substitute it here, you will cancel off j naught lambda and r naught, this j naught lambda and r naught will be nothing but j1 lambda and r, so that and this will get cancelled off. Okay, so it is just a very simple manipulation, and from your theta you can also calculate your d theta by dr at r equal to r naught, which comes to twice summation n equal to 1 to infinity 1 by beta n. So now when you differentiate, you have to differentiate j naught into lambda into r, right. So j naught lambda into r, as I said, that is nothing but minus lambda n j1 lambda n r. Okay, so that will put a minus sign here, so this will be lambda n j1 lambda n r, and at r equal to r naught this will be at r naught divided by, you already have j1 lambda n r naught into e power minus 4 beta n square x by d by Beckley number. So once again these two will cancel off, and if you substitute your derivative as well as your mean temperature into this expression, let me call this as expression number 2. So this will give me Nusselt number substituting for theta m and d theta by dr at r equal to r naught into 2. The final expression, I think if you cancel off some common terms which is straightforward, you can do that, you will get minus 4 beta n square into x by d by Beckley number divided by summation n equal to 1 to infinity beta n square power minus 4 beta n square into x by d by Beckley number. Okay, this is the final expression for Nusselt number as a function of x. Okay, so all you are doing, you have this theta m, you have taken the derivative of theta with respect to r at r equal to r naught, just you substitute into this, it is a very simple manipulation, just one step, and then you finally get the expression for nux. So as you can see, it is a function of only x, therefore all the functions of r have cancelled off, you have only variation with respect to x, and these summations are separate in the numerator and denominator, you cannot simply cancel this term here. Okay, so this is a separate summation, this is a separate summation. Okay, now this is a general expression for the for fully developed hydrodynamically and thermally developing flow. Okay, now we should asymptotically retrieve the case for thermally fully developed flows from this expression. What is the asymptotic case? What is the limit at which we can retrieve the fully developed case? When your x by d goes to infinity for large values. Okay, so for large value, or you can say for large values of x by d by Beckley number, or you can just simply say for large values of x by d you go asymptotically, because you now are in the thermal entry length region. So if you keep going down further and further and further, okay, so somewhere, so you have your thermal boundary layers will be meeting somewhere here, so now your x is somewhere here. So if you go to large values of x, okay, so that will give you asymptotically, it will reach the limit of thermally fully developed flows. So in that limit what happens is, see these values of beta n will be smaller and smaller as you go for larger values of x. So therefore we retain only the first value of beta, that will be the most dominating term. Okay, so only the first term will be significant when you look at large values of x by d. So that will reduce this to nu going to x by d going to infinity. This will reduce to just beta 1 square. Okay, for large values this anyway will cancel off. You have this going to 0, this going to 0, you have only in the denominator 1 by beta n square, and only the first term will be the most significant term. Okay, so that if you substitute the value of beta 1 square as 2.4048 the whole square, that comes out as 5.783. Okay, so this is the limiting solution for thermally fully developed flows with, this is your limiting solution for thermally fully developed with flux flow. Whatever we have derived earlier was with a parabolic flow. With a parabolic flow, constant wall temperature boundary condition, what was the Nusselt number? 3.6. So now this is much higher than that value, because now instead of parabolic profile you have a uniform profile everywhere. You see, wherever you take the profile. So now what is the significance of a uniform profile? Earlier when you had a parabolic profile, near the wall the velocities were small, so due to that the heat transfer coefficient is smaller. Now when you replace that with the parabolic with the uniform plug flow profile, the velocities are very high near the wall, and this will improve the convective heat transfer. So therefore you see the Nusselt number has gone up like anything. Okay, the same thing if I had asked you to do, instead of a parabolic profile with a plug flow for the thermally fully developed case, you would have reached the same value. So that you are reaching as an asymptotic limit to the thermally developing flow. Okay, rather than doing the thermally fully developed flow, we could do this and then we can go for large values of x by d and directly get the limiting solution. So tomorrow, so this is the classical Graetz problem that he did, that he assumed a plug flow and then he did it. So tomorrow what we will do is we will do an extension of Graetz problem. So we will do the extension first to parabolic velocity profile. So then you should reach the value earlier what you got, 3.6. Okay, and the next we will look at the extension of Graetz problem to other boundary conditions like constant wall flux as well as linear variation. So I have already posted a particular solution manual in the website. That is basically an extension of Graetz problem by Sellars. The 3 people who did this extension work, and it is original classical work in 1954, and we look at some of that solution as well. Okay.